Hi guys, welcome back. This is Professor Hank, and in this video I'm going to walk you through a basic algorithm for how computers do integer division. Okay, so let's go ahead and begin. Okay, to start off with, we're going to have to talk about some terms, right, just to remind you of what these different things mean. So if I'm dividing a couple of integers, or if I'm dividing an integer by another, right, the dividend is what we refer to when we talk about the number being divided. The divisor is the number we're referring to when we're talking about what's dividing the dividend. The quotient is going to be the primary result of the division, but don't forget we also have the remainder, which is the second result, right? So if I'm dividing 5 by 2, then the dividend is 5, the divisor is 2, the quotient will be 2, and the remainder will be 1. Right? So the grammar school algorithm that you learned tries to see how big of a number can be subtracted, creating a digit of the quotient each time. The division algorithm the computer uses is going to be similar to this. So this is going to require that we set up a quotient register set to 0, a divisor register, which will be initialized in the upper word with the divisor, and a remainder register initialized with the dividend. So here's the algorithm that we're going to be following. Once we've got all of the registers set up, then the algorithm flows like this. We start by subtracting the divisor register from the remainder register, and we place the result in the remainder register. Then we test the remainder. If the remainder is greater than or equal to 0, then we're going to do a shift. We're going to shift the quotient register to the left, setting the new rightmost bit to 1. If the remainder is less than 0, then we restore the original value by adding the divisor register to the remainder register and placing the sum in the remainder register. In addition, we shift the quotient register to the left, setting the new least significant bit to 0. Regardless of how that test turns out, we then shift the divisor register to the right 1 bit, and we're going to go through for 33 total repetitions if we have 32-bit registers. As if we had 64-bit registers, we would need 65 repetitions. Now in the example I'm going to show you, I'm going to use small numbers, which will have fewer bits, so that way it won't take forever, and you won't have to suffer through watching me write numbers for hours upon hours upon hours. But it's just something to keep in mind that the number of repetitions is going to be the number of bits you have in your registers plus 1. Okay, so let's see a simple example here. Let's say that we're going to go ahead and divide 10 by 3. Right? Just want to keep it short and simple. 10 and 3 are going to have very few bits we have to keep track of. So it'll be able to give us enough to see how the algorithm works without having to be too tedious. Okay, so 10, if we convert that into binary, is going to be, we're going to need a 1, or excuse me, we're going to need an 8, we're going to need a 2, and that's going to give us 10 in binary, right? So the 3, we're going to need a 2 and a 1, okay? Now once we have that converted, we have to set up some registers. So we're going to need a register for the divisor, okay? And that register is going to get initialized. And here's the thing, the divisor register needs to be twice as big as the other registers. And the divisor is going to be initialized in the upper half of that register, right? So that 3 is going to go in the upper half, right? So we're only using nibbles here, which means that, we're looking at, the size of this, just nibbles. So the divisor register in this example would only need to be a byte long. Okay, in addition to that, we're going to need a remainder register, and we're going to need a quotient register. Okay, quotient. And the quotient register gets initialized to 0, and the remainder register gets initialized to your dividend, right? So to the 10. Okay. Oops. Let me go ahead and fix that. So to the 10. 1, 0, 1, 0. Okay, so let's go ahead and walk through the example. So in this example, I'm using 4-bit registers, right? So the quotient register is going to be 4-bit, the remainder register is 4-bit, and remember the algorithm calls for the divisor register to be twice as big as the other guys. So for this example, it would be 8-bit. Now if you had, on your computer, if you had 32-bit registers, which is what MIPS uses, then that divisor register would have to be 64 bits. But remember, there are no 64-bit registers, so it would be they'd be using the high and low registers. But anyway, so this algorithm calls for a number of repetitions that's equal to the register, the 4-bit register, plus 1, right? So we're going to have a total of 5 repetitions, okay, of this algorithm. For MIPS, it's 33 total repetitions, right? Because they got 32 registers, or 32-bit registers plus 1. Okay, so the divisor register is currently set at 48. The remainder register is 10. And so let's begin, right? So the algorithm for each repetition, you subtract the divisor from the remainder, okay? And if the difference is greater than or equal to 0, then you update the remainder register with the difference. Okay, well, in this case, 48 minus 10, or excuse me, 10 minus 48, negative number. So the remainder register remains unchanged. And once we've had that determination, right, then we do some shifting. Since the remainder register doesn't get updated, shifting comes next. So divisor register shifts to the right 1 position, and the quotient register shifts left 1 position. That's the end of the first repetition. So we're going to start the next repetition. The divisor register currently has 24 in it. Quotient and remainder remained unchanged. So if we subtract 24 from 10, that's a negative number. Therefore, the remainder register remains unchanged. So let's go ahead and do our shifting. Okay, so we shift 1 position to the right for the divisor register, making it 12. The quotient register gets shifted 1 position to the left, and that's the end of that repetition. Okay, so the next repetition begins. Subtract divisor from remainder, negative number. So remainder register remains unchanged. Then we have to do our shifting. So divisor shifts 1 place to the right, and that becomes 6. Quotient 1 place to the left, still 0. End of that repetition. Okay, start the next repetition. We subtract the divisor from the remainder. Now we're going to see some interesting things happen. So 6 minus 10 is 4, and since that's 0 or greater, we're going to update the remainder register to what? To the difference. So the difference is 4. So the remainder register is going to become 0, 1, 0, 0, which is 4. And then we do our shifting. So the divisor register shifts to the right 1 position, as it has been. Okay, and so that's going to leave us with 3 in the divisor register. The quotient register is going to shift 1 position to the left, but instead of the new value being 0 in the least significant digit, it's going to be 1. And so that is the end of that repetition. Okay, so the next repetition begins, and we subtract the divisor for the remainder. So 3 minus 4 is 1. That's greater than or equal to 0. So the remainder register is going to get updated to the difference, okay, which is 1. Then the shifting happens. The divisor shifts to the right 1 position, and the quotient register shifts to the left 1 position. The quotient register's least significant bit becomes 1. Okay, and that ends that repetition. And once that repetition is over, we have our 5 reps, and the algorithm comes to an end. So what are we left with? What's in the quotient register? 3. What's in the remainder register? 1. 10 divided by 3 is what? 3, remainder 1. Okay, so that's going to bring this video to a close. If you felt that the video was useful, please consider giving the video a thumbs up. And if you thought that the video sucked, well, then you've got that thumbs down button as an option as well. If you'd like to see more videos, if you're interested in more content from the channel, feel free to hit that subscribe button. And as usual, if you're a student of mine and you have further questions, feel free to drop me an email or to stop by my office hours. Okay, thanks for watching, and we'll see you next time.